Hello students. So today in this video we are going to start with the next module that we are going to start with center of mass. Right. So let's start center of mass. Center of mass. Okay. So first, what is center of mass? Okay. So center of mass for a system of particles. Let's understand center of mass of a system of particles. Okay, system of particles. Okay, so let us say we have so many particles. Let's say this is one particle, this is another particle, so many particles are there, right? All these particles will have different characteristics. So with respect to a particular coordinate system, let us draw a particular frame of reference x, y, z. This is the origin 0, 0, 0. So with respect to this, let us say that this is the first particle. This is the first particle, this is second particle, this is third, fourth, fifth, sixth, so on. And let's say this is the nth particle. So we are taking n number of particles. Now, first of all, each of these particles have different position vectors. You can see that when you draw this, this will be the position vector. When you draw a straight line like this is the position vector of first. Similarly, this will be the position vector of second, and so on, right? Each of them have position vector. Each of them will have some velocities. Let's say its velocity is v1, its velocity is v2, its velocity is v3 vector, and so on, right? Similarly, they will have some acceleration a1 vector, acceleration of the second particle a2 vector, acceleration of third particle a3 vector, so on. So each of the particles can have their independent, motion, independent kinematics. Now, to study the entire system, we want to reduce this whole system of particles into a single particle, and each particle has, let us say, masses also. So each particle has, let's say, mass m1, and second particle has mass m2, third particle has mass m3, and so on, right? You want to reduce the entire system into a single particle, and that single particle should possess the mass of the entire system. Okay, so if you want to reduce, let us say that I am going to give a particular center of mass. Center, that is what is center of mass. So this is a single particle which will represent the entire system. The entire system mass is concentrated at this point. So this point is called center of mass. Center of mass. So what is this center of mass? So center of mass is a single point mass which represent the entire system. The total mass of the system is concentrated here. Okay, that's what is center of mass. So center of mass is the total mass, is the location, you can say it is the location where the total mass of the system is supposed to be present. So why we want to reduce the entire system to a single particle, so that we can just study the characteristics of center of mass. Okay, because we can just study only one mass. That's how we can do it. So that means the mass, total mass m1 plus m2 plus m3 all the sum of masses up to, let's say, n particle, this m is the mass of center of mass. Center of mass means that's the total mass. Okay. Now here we need to understand where is its location, where its location will be. So it will also have some position, right? So if you join from this origin to this with respect to the same, it will also have some position vector, it will have its own velocity vector, it can have its own acceleration vector. So all this, when you are going to study about the entire system, it can be represented by a single particle which is center of mass, and its position vector, its velocity vector, its acceleration vector. We should know how to calculate, right? So let us first write down the important formulas for center of mass. Position vector r center of mass. So r center of mass will be given as m1 r1 vector plus m2 r2 vector plus dot dot dot, in same manner mn rn vector, divided by the sum of all the masses. That means the total mass of the system, you can see. Okay. Similarly, the velocity of center of mass will be calculated as m1 v1 vector plus m2 v2 vector plus dot 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 plus mn vn vector, divided by the total mass. Same way, acceleration vector of center of mass will be calculated as m1 a1 vector plus m2 a2 vector plus dot 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 plus mn an vector, divided by the total mass. Okay, so this is how we can calculate that single particle. And of course, if you are taking this is in terms of vector, that means it includes all the 1 dimension, 2 dimension, 3 dimension, everything. But if you want to just write in 1 dimension, let us say only x-axis you want. Suppose, for example, you take a system of two particles. Suppose we have a system of two particles, and let's say the two particles are lying along x-axis, isn't it? So you can take that one of the particle is here, another particle is here. They are only lying along x-axis, so they will have only x-coordinate. So you can say this x-coordinate is x1 and its x-coordinate is x2, and its mass is m1, its mass is m2. So definitely the center of mass will lie somewhere in between, right? Somewhere in between the center of mass will lie. Okay, now the thing is that what is the coordinate of center of mass? So if the coordinates of the individual masses are given, the total center of mass coordinate we can calculate, which is x is equal to x center of mass. So this x center of mass can be calculated same way, m1 x1 plus m2 x2 divided by total mass we can do, right? Same way, velocity of center of mass can be calculated as m1 v1 plus m2 v2 divided by total mass. Similarly, acceleration of center of mass can be calculated as m1 a1 plus m2 a2, right, divided by total mass. Remember, here the accelerations, velocities, positions all are one dimensional, right? If it is in y-axis, so instead of x you can replace it with y, and similarly if it is in z, so you can calculate instead of x z. So everything will remain same. Now let us take this simple case. Suppose if I want to find the position of center of mass from first particle or from second particle, how to do that? So we should know for this case, very simple case. Suppose there are two particles and the masses are m1, m2. Let us say I want to find where the center of mass is. So let us keep first as origin. If I am keeping this as origin, so x1 will become 0 and x2 will be let us say d, because d is the distance between them. Let us take this distance as d. So now we can calculate x center of mass. X center of mass is m1 x1 plus m2 x2 by total mass, which is, you can write m1 plus m2 total mass. Now here x1 is 0, so you will be left with only second term, m2 by m1 plus m2 into the total distance. So what is this? This distance is nothing but from the first particle. Similarly, we can calculate the distance from the second particle. So let us say now I am going to write this as r1 r2, r1 r2. So this I am writing this as r1, distance from the first particle. Similarly, distance from the second particle r2 will be m1 by m1 plus m2 into total distance. So we must remember these two important formulas, right, for a system of particles. Okay. Now what about bodies which are continuous? Bodies which are continuous. So bodies can be continuous, right? So for continuous bodies, we have to use integration. So x center of mass we can calculate by integrating, right, x into dm divided by total mass, which is integration. Similarly, y center of mass will be calculated as integration of y dm by integration of total mass. Similarly, z center of mass can be calculated as integration of z dm by total mass. Like this we can calculate. So what is x, y, z here? So suppose this is a body, okay, any body is there, and you take a elemental mass. This is a very small mass dm, because the body is continuous, right? So you take a small mass dm on the body. Now with respect to the given coordinate system, so some coordinate system will be there, isn't it? X, y, z. It will have some coordinates x, y, z. So that's what we are doing. This x, y, z is nothing but the position of the element that we are choosing. That x, y, z is the position of that element, okay, and then we are going to integrate. Of course, here integration of dm is nothing but the total mass, okay. This is the total mass of the entire system, okay, right? So we can do that. So let us take a very simple cases I will discuss here. So let's take first of all, one thing we should note that the center of mass can lie inside, on, or outside the body. So if we are taking a system where continuous bodies is there, continuous mass is there, so center of mass can be inside, on the body, or outside, anywhere it can. It's not necessary that there should be some mass present on the center of mass, okay. Mass may or may not be present at the center of mass, okay. So these two things we should note. Now let's take for symmetric distribution of masses. For symmetric bodies, center of mass is the geometric center, What is geometric center? It is just the center of that body, okay. For example, if you take a ring, suppose if I take a ring means full ring we are taking. So if this is a ring here, full ring, the geometric center is nothing but the center of the ring. So this is the center of mass. Although there is no mass at that center, because all the mass is present on the ring, not at the center, but the entire ring can be supposed to act at the center of mass, which is the geometric center here, because the body is symmetric. Similarly, if you take a sphere, suppose you take a sphere. So in a sphere, what will happen? The geometric center is the center of mass. Of course, it can be hollow or it can be solid. It doesn't matter if a sphere is hollow or if the sphere is solid. In both cases, because it's completely symmetric, so the total mass will lie at the center of mass. Okay, that's the center of the sphere, right? So in this manner we can say, like for example, if we have a rod, uniform distributed, mass is uniformly distributed, so center of the rod is the geometric center here. So center of mass will lie here, exactly at the midpoint. But of course, if the rod is not uniformly distributed mass, then it may be somewhere, but it may be between here or there, it may be anywhere, right? So that we will calculate for such bodies. Okay, so we should know about this concept of center of mass. Then for other kind of figures, let us note where the center of mass will lie for different type of figures. That means which is worth remembering, right? That things I will mention here, some important results. So let's note that for circular disc also it will be center. So leave that which is completely symmetric. Now let's take things which may not be very much symmetric. Okay, so let us take for example a first case is hollow cone. Let's take hollow cone. If you take hollow cone, where will be the, let's say this is the hollow cone, like this. Okay, so where will be the center of mass for a hollow cone? Okay, so center of mass of hollow cone is h by 3 from the base. So the center of mass, so from the base h by 3, where h is the total height. Total height is h, it will lie at h by 3 distance from the base. Okay, so we should note that center of mass h by 3 from base. So from top it is 2h by 3, right? 2h by 3. Similarly, let us take next. If I consider a solid cone, then what happens in case of solid cone? If it is a solid cone, previously it was hollow, now it's, let's say, solid. Okay, so some mass will be there, it will be distributed over this body completely, solid, no cavity is there, like this. So where will be the center of mass of this body? So center of mass of this body will be h by 4. So it will be lying more closer to the base. Okay, it will lie here. Center of mass will now lie at h by 4. Total h is the height. Now it will be h by 4. Okay, next let's write down the result for the next figure. So what about if there is an arc? Let us say there is a circular arc. This is a general formula I am giving. So circular arc means, let us say, like this. Some arc is there. Okay, mass is present. It's like a part of a ring. Okay, part of a ring. So there will be center here. Center of the ring will be here. Okay, but this time it is not going to be the it's because it is not the geometric center as well. So we need to find out, and it will come somewhere here on this axis of symmetry. So first of all, the center of mass will lie on the axis of symmetry. This is the axis of symmetry. So on this axis, center of mass is going to lie here. And how to calculate the distance of center of mass from the bottom? Okay, bottom means from the center of the ring. Okay, this distance you want to calculate. That is the distance of center of mass. So how do we calculate this distance? I will write directly the formula 2r by theta sine of r means here sine of theta by 2. Okay, sine of theta by 2. This we should know. What is theta? Theta is the total angle here. Total angle. So now you can take a semicircular ring. Take example a semicircular ring. Take example a semicircular ring. If you take a semicircular ring, it will be like that. The angle now will be 180 degree, right? This angle becomes 180 degree. So in this case theta becomes 180 degree. Now you can see the symmetric axis is this. This is the symmetric axis, right? So center of mass will be lying here. So what is the distance of center of mass? 2r by pi, right? Because sin 90 becomes 1 and theta will be pi. Pi means we have to keep theta in radian, okay, not in degrees. Okay, so this is what it is going to be. So here the distance of center of mass becomes 2r by pi. Like this we can calculate for any length, any part of the arc we can take, right? Then let's go to next result number 4. Now if we have a disc, what will be for this? So semicircular disc I will take, semicircular disc. If you take semicircular disc, that means mass is distributed like this. Okay, the total mass will be distributed over the disc like this. So for semicircular disc, where will be the center of mass? Let's calculate the center of mass. So from the center of the disc, again it will lie on the axis of symmetry. This is the axis of symmetry. Axis of symmetry. So where it will lie on the axis of symmetry? So it will lie, let's say, here. So this distance from the base or from the O, that distance is going to be 4r by 3 pi. This we have to remember. Otherwise we need to derive it again. Okay, 4r by 3 pi. Similarly, if I take a solid hemisphere, So if you take a solid hemisphere, let's say it's like this, right? It's a solid hemisphere. So masses are distributed in the body, right? Like this, let us say. Okay, so now here again the axis of symmetry will be the axis passing through the center of this. Center is O and center of mass will lie somewhere here. This is the center of mass. So how much distance center of mass will be from O? That we should know, that is 3r by 8. 3r by 8. Okay, 3r by 8. And what will happen if it is hollow? Okay, let us say hollow hemisphere. Hollow hemisphere. So in case if it is a hollow hemisphere, it's completely hollow, right? It will be like this, completely hollow hemisphere. The state of diagram. Again the axis of symmetry only it will lie. This is the axis passing through center. So this time the center of mass will lie at a distance of here. This distance will be r by 2. Okay. So in this manner we can calculate all this. We should know all these formulas, right? Then What about semicircular annular plate? That also you note. Semicircular annular plate. What is that semicircular annular plate? That means it is like a semicircular plate, but there is two different radius. There will be inner radius, there will be outer radius. Okay, so in such cases, let's say this radius is R1, outer radius is R2. Okay, two radius are there. Then where do we get the center of mass? Center of mass again will lie on the axis of symmetry, and let us say center of mass is here. Center of mass. So what is the distance of the center of mass from O? This distance. Okay, so this distance can be calculated as 4 by 3, and in the numerator R1 square plus R1 R2 plus R2 square divided by 3, and this time there will be pi, 3 pi, and here it will be R1 plus R2. We can remember this. Okay, suppose the R2 is large and it is a very thin, then R1 can become 0. Then it will be like, the formula for 4R by 3 pi, isn't it? So we should remember this center of mass for important figures. I think this will be sufficient. Other figures we can do it ourselves, right? Then let's go to the next. So sometimes there will be addition and subtraction of mass. So when two masses are added or one mass is subtracted from there, we can just calculate like that. Okay, so in addition there are two cases you can take: addition and subtraction. So what will be the center of mass in case of addition? So suppose two bodies are added, right? So it will be center of mass will be resultant bodies m1 x1. Here x1 will represent center of mass of first. Similarly x2 m2 x2 by m1 plus m2. Similarly the y coordinate. In the case of subtraction, x center of mass of the remaining, because you are subtracting one body from other. So let's say the big body you are subtracting small body. So m of big, x of big minus m of small, x of small divided by m of big minus m of small. This is what you have to remember. Okay, so with these formulas you will be able to work out questions on center of mass concepts, right? So center of mass concept problems we will see previous year questions, right? So thank you for your attention, and we'll see in the next video.